This is Mrs. O'Neill for AP Chemistry, Chapter 19, Section 5, Gibbs Free Energy. You should have watched the intro lesson. I believe this was one of his earlier videos, so these are the notes that I took. Free energy really is available energy. It's the amount of energy that can be used to do work. So he's going to relate this equation where Gibbs free energy equals enthalpy, that's your delta H, minus temperature at which the system is at, and your entropy, right? How easily it is to go towards disorder. So he talked about a ball rolling down a slide, and of course what's going to happen to the total energy of that system? Well, H is going to decrease. And he also is going to show you later on that energy diagram where here's your reactants and your products are all the way down here. Your products always have less energy than the reactants it comes from, exothermic. Then he gave you an example of diffusion, and he said, let's say if we take something like something in our liquid and make a solution. So I'm not going to talk about salt because that's like breaking up of the particles, but I guess you can kind of look at it that way. Or you can even look at it something easy like putting food coloring into water. When you put a drop of food coloring into water, it's going to disperse out. Why does it go towards disorder? Because S is increasing, and of course randomness naturally goes towards disorder. So that S is going to increase. And then he talked about the increase in temperature for an explosion. So those are your three components of that equation. So then he said, let's look at that equation and let's analyze it. This is a really, really good part that I like. So if we look at all of this and we took delta H and we decrease it, what's going to happen to X? Well, it's also going to go down. It's also going to decrease. What happens if we increase our temperature and increase the disorder? Again, what happens to X, or what happens to our Gibbs free energy? It's going to go down. Again, because of that minus, right? We're subtracting both of those multiplied together. So if we go back to those examples, again, what's he doing here? He's talking about delta H decreasing, and so delta G is also going to decrease. And if he talked about diffusion, he talked about increasing in entropy, increasing in disorder. So what's going to happen to our delta G? It's also going to go down. And how about temperature? How does this affect temperature? Well, when we increase the temperature, our delta G, Gibbs free energy, goes down, decreases. So what's going to be spontaneous is delta G being less than 0. If delta G is a negative number less than 0, it's going to be exergonic or exothermic, and it's going to be a spontaneous reaction. So I know I've talked about delta S being spontaneous before, but now delta G really gives us the overall, is the reaction, is the process going to be spontaneous or not? If delta G is greater than 0, if it's a positive number, it's going to be endergonic and it's going to be not spontaneous. So in equilibrium, delta G is 0. Remember, we always need that standard. We always need somewhere where it's going to be either positive compared to 0 or negative compared to 0. So again, here's our two examples. Again, he gave us respiration and photosynthesis. So here we have an exothermic reaction where our products have less energy than our reactants. And here we have an endergonic, like photosynthesis, where our products have more energy than the reactants it came from. So again, he just kind of showed a nice little diagram, or maybe I got this from the web, where photosynthesis you have to move up and respiration you have to move down. But really the reaction is, again, going to be spontaneous in one direction and not spontaneous in the other. But it really comes down to that free energy, how much energy is available to do that work. So again, negative G is going to be spontaneous because it's like that ball rolling down the hill without any aid. That's the other thing, right? It doesn't need any help. If you put that rock as close to the edge as you need to, you don't give it a shove, eventually it's going to roll down all by itself. But a positive delta G is a non-spontaneous direction. So it needs a lot of work, a lot of energy to get that ball back up that hill. So now to your notes packet, and in this section, your objectives is going to, again, encounter this another thermodynamic state function. It's a state function because of that delta sign, right? We just need to know the final and the initial. You don't really need to know the path at which it took. And this is a measure of how far removed a system is actually from equilibrium. Is it going towards the left of equilibrium or to the right of equilibrium? Equilibrium is where delta G is 0. And we need to know the change in free energy measures the maximum amount of useful work obtainable from that process. And it tells us the direction in which that reaction is going to be spontaneous. So pause, fill in the blanks, and then play to hear my words. Again, that free energy is just how much energy is available to do that work. So we want to remember that work and energy really do have the same units. And as you write in your blanks, you should be reading as well. So these are all different examples of what work is or how work can be done to a system or process. Fireworks display is usually the result of highly spontaneous reactions that release a large quantity of free energy. This reaction, or these reactions, require a very high initial temperature to produce the fast reaction rate observed. So one thing I want to remind you is that yes, it's spontaneous, even though we have to give it a little kick, right? We still have to light the firework in order for it to go up into the air and explode. So just because we say spontaneous reaction, remember, that doesn't mean it's going to always go 100% on its own. Sometimes you have to give it a little kick in order for it to then do what it needs to do. But ultimately, that is spontaneous. It doesn't take too much energy to light a wick and have that little spark make the firework explode into the air. It would, however, take a lot of energy to take all those little pieces of that firework that exploded and put it back into the canister it came from. So if we look at a spontaneous reaction, occurs naturally and favors the formation of products at a specific condition. So here we have something like cadmium sulfide forms spontaneously. So cadmium sulfide is the yellow precipitate that forms when a solution of your sodium sulfide and cadmium nitrate come together. So is free energy released in this reaction? Yes, because the reaction is spontaneous. This happens on its own. We take those two solutions, we mix them, and that precipitate comes on its own. Now, it's going to take a lot of work, and it's not going to be spontaneous going the other way. We can make it go the other way. We can force it going the other way, but it's not going to do it on its own. But if we look at something like this is a non-spontaneous reaction in which the reaction does not favor the formation of products at specific conditions. So many non-spontaneous reactions are required for a plant to grow. Non-spontaneous reactions can occur when they are coupled with spontaneous reactions. And we're going to talk a little bit more about coupled, I believe at the very, very end of section 7. There's an extra video, like a closing video, and it talks about these coupled reactions, how one reaction has to be coupled with another one. They have to kind of do it at the same time in order for the reaction to occur. So what is another requirement then for this photosynthesis reaction to occur? Well, if we look here, carbon dioxide and water to form the glucose and oxygen is not going to happen on its own. If you notice, it needs light energy. It needs something from the sun in order for those leaves to grow. And that should make sense. In the wintertime when there's not as much light, right, that's why, or I should say in the fall and winter is when they die because there's not enough light. It needs a certain amount of light energy from the sun in order for the reaction to go the other way so the plants can grow nice green leaves. So this is the guy, Mr. Gibbs, and again, this is the very first American scientist that you probably heard of. There's not too many out there, at least not that late in the 1900s there. There wasn't too many American chemists that came up with anything, so he was considered the father of physical chemistry, and he was from Connecticut, so I thought that was pretty interesting. So again, Gibbs free energy is the maximum amount of energy that can be coupled to another process for useful work. So is there a way then to use that delta H and delta S to predict if the reaction is going to be spontaneous? Of course there is. That's why I showed you that video as an introduction. So you know, if we know the delta H value, and if we know the delta S value, and if we know the temperature, or we can predict if that reaction is going to be spontaneous. So again, this is on your reference sheet. You already know delta H, enthalpy, that's going to be exo or endothermic. You know T stands for temperature, always in Kelvin. And delta S is entropy. Is it going towards disorder, right? Nature tends to go towards disorder. So this is where it gets a little kind of confusing, but again, here's our equation, but it gets a little confusing with all the signs. So we want to remember if temperature and pressure are constant, delta G negative is going to be spontaneous because the system loses free energy. 0 is at equilibrium, and positive is not going to be spontaneous in the forward direction, but then that means that it's going to be spontaneous in the reverse direction. So again, here's our exothermic reaction, right? Reactants forming products. Our delta H is going to be negative, and we're going to say our delta S is going to be positive because it's going towards disorder. So here's our spontaneous reaction, right? That ball rolling down the hill, lots of kinetic energy. Guy got to get out of that way. And then here we have free energy decreases, though, until equilibrium is obtained. But then it's going to require an increase in free energy. So again, here's our reactants and here's our products, but they're now showing you the amount of energy that is needed for that equilibrium and to get back over. So it's kind of the opposite of a reaction diagram. And of course, this would be not spontaneous. That ball's never going to roll up the hill without having any kind of energy pushing it up. So again, to be spontaneous or not to be spontaneous. So we have exergonic reaction, endergonic reaction. There's your exothermic versus endothermic. So give it some thought. Hopefully you came up with that information. So again, what does that little symbol mean? We've seen that many times. That means it's under standard conditions. And here I'm giving you some examples of what standard conditions really are. So you've seen this before many times. Again, here we have our products minus reactants. We have the value going to be multiplied by the coefficient in the equation. So can you answer these questions? And again, there's that word coupled, and we'll talk about more about that later on. And see you in class. Hopefully you got those answers.